This video is prepared by Avya Classes. Please subscribe the channel, raise your doubt and watch the video for sure success in JEE, AIMS and NEET. So now we will calculate the expression for the elastic potential energy in case of spring. So first thing we should learn that spring force is a conservative force. So how we will prove that any force is a conservative force? For a conservative force, the potential energy stored in the process depends upon the final point and the initial point, or the work done by the system in case of conservative force will depends only on the initial point and the final point. So we will see that if the initial point, suppose if I take a spring and stretch it by a distance equal to x, so the change in, and we term this point as a point A, this point as a point B. So the work done or the potential energy stored will depends on the potential energy at the point A and B. So potential energy of the system, of the whole system, or in the process, or we may call it as a work done, it is equal to UB minus UA. And it's immaterial that what path we follow. We can take A to a next point C, and then if we come back to a point B, still the work done will be, net work done will be, or the potential energy will be equal to UB minus UA. Second thing is that for a conservative force, the work done in a closed path will be equal to 0. So if I take the spring and stretch it from the point A to the point B, after that we just move to its original point A, then the work done in the whole process, that is from going A to B then to A, that is work done in the process A to B to A, will be equal to 0. So these two are the property of conservative force, and the work done against any conservative force will be stored in the potential energy, which we have learned already. So first thing is that the work done in the conservative force, or work done against the conservative force, work done against the conservative force will be stored as potential energy, and in case of spring, the work done against the spring restoring force will be stored as a potential energy in the spring. So we will first calculate what is the elastic potential energy of the spring. So how we will calculate it? So it is written here, when a spring is stretched or compressed from its normal position x is equal to 0, then work has to be done by external force against the restoring force, and work done by this external force will actually stored in the spring as a elastic potential energy. So what is the value of this external force? So to calculate the value of or the work done by this external force, we just assume that the external force is applied in such a way that it will produce a zero velocity, or it will move the object with a very slow velocity, and because of this there is no energy there is no energy associated for the kinetic energy. So we will consider only potential energy in this whole process. So what will be the force in this case? So we will apply the external force F external such that it will just counter the spring restoring force. So the external force will counter the spring restoring force in order to calculate the value of elastic potential energy. So F external is equal to F restoring, and it is equal to Kx. Now we will calculate the work done in case of this external force from a point A to point B. So how we will calculate? We will calculate the work done in this process. So for this we just take an arbitrary distance x through which the object has already been shifted. So if we expand the spring by a length equal to x, then the restoring force Fsx will be produced. The restoring force is a function of x, and it is given by equal to kx. Now if we move the object by further a small distance dx, then the value of restoring force for this infinitesimal displacement will be taken as constant. So for this case, the restoring force Fs is equal to, it will be a function of x plus dx, and we term it as a constant. For this infinitesimal displacement, we consider the force remain to be constant, and in this case the work done will be given by dw, which is the infinitesimal work done, and infinitesimal work done will be equal to f external dot dx. So as we know that the value of f external and dx will be in the same direction, f external will also towards the positive x direction and dx will also towards the positive x direction as per this figure. So the angle between these two will be 0 degree, and the value of dw is equal to f external into dx. The value of f external is equal to kx, so the infinitesimal work done is equal to kx dx. Now we will have to calculate the work done to stretch the spring through a distance y from its mean position, which is at x is equal to 0. So we will integrate this equation to get the net work done. So how this integration will be done, that as dw is equal to kx dx, so what we will do, we will just take 2 points, that for the first, for the right hand side the variable is dx, so we check the value of x through which we have to move the object. So object is moving from the value x is equal to y, because we have to calculate the through a distance y from its mean position. So the limit of x is equal to 0. So when x is equal to 0, then the object is at its mean position, and if I put the value of x is equal to y, then it means the object has shifted to a distance equal to y. And when the object has its mean position, then the work done will be 0, and when the object has shifted to a distance y, then the work done will be w. And if we integrate it, then we get w minus 0 is equal to k into 0 to y x dx, and the value is equal to k x square by 2 limit 0 to y. So the value comes is equal to k y square by 2. So the total work done to stretch the spring through a distance y from its mean position is given by w is equal to 1 by 2 k y square, and this work done is stored as a potential energy in the stretched spring. So how we get this work done? So as the work done is we have to calculate the work done for this external force, and this external force is not constant, it's a variable. So we just take an arbitrary distance x and make a infinitesimal small displacement dx, and we calculate the infinitesimal work done for this dx, and we get the value of dx is equal to kx dx. Now if we integrate it, we get the total work done to stretch the spring through a distance y, and this work done is stored in the spring as a potential energy. So in this way we just get the formula of work done when the spring is stretched through a distance y. We will also see that the work done when we compress the spring through a distance y from its mean position is given by w is equal to ky square. So whenever we make a stretch of x or the compression of x, the value of work done will be equal to kx square by 2. So work done will be equal to kx square by 2 for x compression or expansion of spring, and this work done kx square by 2 will be stored in spring as a potential energy. So now we will move to next concept, that how we will calculate the work done from the fx graph. So this is basically the fx graph, and we have already learned that in the case of fx graph, the area gives you the value of work done. So as we know that the area, the work done is equal to F dot dx. So this is the area, and this give you, this area gives you the work done. So if I draw the fx graph, then the area give you the work done. So this is the in case of spring, the force will be minus kx, and the area will be given by this. So clearly the work done for stretching the spring through a distance xm will be given by minus kxm square by 2, and this is the work done for by spring restoring force. So I will just show you from for this figure also. Suppose that this is our normal position for which x is equal to 0, and if the spring is stretched through a distance equal to x or xm, then the spring restoring force acts towards minus x direction and given by minus kxm, and the work done for this spring restoring force will be equal to minus kxm square by 2, as the direction of spring restoring force and the displacement will be opposite. While in case of external force which just counterbalance this spring restoring force, then the work done W will be equal to kxm square by 2. So you may note that the difference between value of this value of work done by spring restoring force and the external force. While the work done by spring restoring force comes with a negative sign, the work done by the external force comes with a positive sign. So what is this elastic potential energy? We have already learned that the work done against spring by external forces is stored as the potential energy in the spring, and we have calculated the value of this elastic potential energy which comes equal to half kx square. So as we know that F is equal to kx, so we just put the value of kx is equal to F in this equation, and we get three different formula for potential energy, that is U is equal to half kx square, and it is equal to 1 by 2 fx, and it is equal to f square by 2k. Here x is equal to f by k you have to put to get the third formula. So basically if you can remember the first formula only, then you can derive the other two formula also. Like in the problem, if the force is given, suppose if the force is given and the spring constant is given, then the potential energy, to calculate the potential energy you simply apply the formula U is equal to f square by 2k. Now we will see a different case when the spring is stretched from the initial position x1 to final position x2. Then you have to calculate the work done in this process. Like suppose the spring is initially stretched for a distance equal to x1. So this is our normal position where x is equal to 0, and this is the position which is x1. Now the spring is stretched for a distance equal to x2, or it has been stretched further for a distance equal to x2. So this value is equal to x2. So if you see that in this case the potential energy is equal to half k x1 square, and here potential energy is equal to, so I just term this is as A, this as a B. So UA is equal to half k x1 square, and UB is equal to half k x2 square. Clearly the work done in moving the distance from x1 to x2 will be given by the change in elastic potential energy, and it is equal to 1 by 2 k x2 square minus x1 square. So if I stretch the spring from initial point x1 to the final distance x2, then the work done in this process will be the change in elastic potential energy, and it is equal to half k h2 square minus x1 square.